How do scientists unlock the mysteries of the human brain? This video delves into the fascinating world of brain study methods. From clinical observations to advanced imaging, discover how researchers explore brain functions. Clinical and anatomical methods involve observing patients with brain injuries. These methods also include post-mortem examinations. They provide insights into the anatomical basis of brain functions. However, they are limited to studying patients with existing conditions. These methods cannot manipulate variables or establish causation. However, they raise ethical concerns due to their invasiveness. Non-invasive methods include imaging and recording techniques. They allow the study of brain function without physical entry. These methods are safe and suitable for human studies. However, they have lower spatial and temporal resolution. They are limited in revealing detailed neural mechanisms. Post-mortem examinations analyze brain tissue after death, allowing researchers to study the brain at a microscopic level. They identify structural abnormalities and functional insights, such as signs of disease, injury, or neural degeneration linked to certain behaviors or disorders. These methods provide detailed examination of brain structures, offering valuable information that can't always be obtained through live imaging. However, they are limited to deceased individuals, which restricts their use in ongoing or developmental studies. They cannot investigate dynamic processes or changes over time, such as neural activity or brain function during specific tasks. Functional MRI measures blood flow changes in the brain. It identifies regions activated during specific tasks. This method provides high spatial resolution. However, it has limited temporal resolution. The equipment is expensive and requires technical expertise. EEG records electrical activity on the scalp, using electrodes placed on the surface of the head to detect neural oscillations. It captures overall brain activity and patterns, such as alpha, beta, delta, and theta waves, which are associated with different mental states. This method is often used for studying sleep and cognition, as well as diagnosing conditions like epilepsy and brain disorders. It provides high temporal resolution but low spatial resolution, meaning it can track rapid changes in brain activity but not pinpoint exact locations. EEG is non-invasive but susceptible to interference, including muscle movements and external electrical noise, which can affect signal clarity. They offer insights into cognitive processes with high temporal resolution. However, they have limited spatial resolution. These methods provide insights into anatomical brain functions. They allow direct observation of patients with disorders. Correlations between brain damage and impairments are revealed. However, they are limited to patients with existing conditions. They cannot establish causation or manipulate variables. These methods are limited to studying patients with brain damage. They cannot manipulate variables or establish causation. Observations are restricted to existing conditions. They provide insights but lack experimental control. These limitations affect the depth of understanding. Invasive methods allow precise control over experimental conditions. They provide detailed information about neural mechanisms. These methods enable direct manipulation of the brain. However, they raise ethical concerns due to invasiveness. Their applicability is limited due to potential harm. Balancing ethical concerns with research needs is crucial, especially in studies involving human or animal participants. Ethical concerns limit the use of invasive methods, such as brain surgery or deep electrode implantation. to protect participants from unnecessary harm. They are applicable to a narrow range of studies, typically where the potential benefits outweigh the risks. Potential harm to subjects restricts their use, as researchers must adhere to strict ethical guidelines and obtain informed consent. These methods provide detailed insights, but at a cost, often involving physical risk, emotional distress, or ethical controversy. Non-invasive methods are safe and suitable for human studies. They provide valuable information about brain activity. These methods offer insights into connectivity and function. However, they have lower spatial and temporal resolution. They are limited in revealing detailed neural mechanisms. These methods have lower spatial and temporal resolution. They are limited in revealing detailed neural mechanisms. Non-invasive techniques provide valuable insights but lack depth. They are suitable for broad studies, but not detailed analysis. Balancing safety with research needs is essential. Post-mortem examinations allow detailed brain structure analysis. They provide insights into physical basis of cognitive functions. These methods reveal structural abnormalities. However, they are limited to deceased individuals. They cannot investigate dynamic processes or changes over time. These methods are restricted to studying deceased individuals. They cannot explore dynamic processes or functional changes. Post-mortem examinations provide structural insights but lack temporal data. They are valuable for anatomical studies but limited in scope. Understanding their limitations is crucial for research. Functional MRI offers high spatial resolution and is non-invasive, making it ideal for mapping brain activity with precision. It allows observation of brain activity during tasks by detecting changes in blood oxygen levels, known as the BOLD blood oxygen level dependent signal. This method provides valuable insights into functional areas, helping researchers understand which regions are involved in processes like memory, emotion, and decision-making. However, it requires expensive equipment and expertise, including advanced software and trained personnel. Balancing cost with research benefits is important, especially in large-scale or long-term studies where resources may be limited. Functional MRI has limited temporal resolution. The equipment is expensive and requires technical expertise. These factors can limit accessibility and use. Despite its strengths, balancing cost and research needs is vital. Understanding its limitations helps in effective application. EEG provides high temporal resolution and is non-invasive. It captures rapid changes in brain activity. This method is widely applicable and safe for human studies. However, it has low spatial resolution and is susceptible to artifacts. Balancing strengths and limitations is key in EEG studies. EEG has low spatial resolution and is prone to interference. It captures overall brain activity but lacks detail. These limitations affect the depth of analysis. Despite its strengths, understanding EEG's limitations is crucial. Balancing strengths and limitations enhances research outcomes. ERPs offer high temporal resolution and sensitivity to cognitive processes. They are non-invasive and suitable for perceptual studies. These methods provide valuable insights into cognitive functions. However, they have limited spatial resolution. Understanding their strengths helps in effective research application. In conclusion, combining techniques helps overcome individual limitations, allowing researchers to gain a more comprehensive understanding of the brain. Understanding the strengths and weaknesses of each method is crucial, as it guides appropriate selection based on research goals. This knowledge drives meaningful research and advances in biopsychology, leading to deeper insights into brain function, behavior, and mental health. Thank you for watching this video.